So let me briefly continue with what we talked about. I want to, maybe it's worth saying a few words about the experiment that we talked about before. Erase this here. So last time we showed an example of electrons bombarding a crystal, and the crystal simulates a diffraction grid. It simulates reflection at discrete points where the atoms are located, and the light is reflected off the crystal, and at certain magic angles we get constructive reinforcement, as we saw with X-rays. So we had some problems in the homework, or you did, regarding that, and you got some experience. And the upshot of this was that when we talked about this crystal experiment, that if we had electrons that are directly hitting the crystal, there are certain magic angles, we'll call them magic angles, where all the electrons get reflected, and they only get reflected at certain angles, theta, which satisfy that d times sine theta is equal to lambda, because, or lambda times m, because this there's a path difference between adjacent rays, or rays of reflection. And this path difference, let's see if I can draw a different. This path difference is what we call d sine theta. Right? That's the extra path difference. And we said last time that there was a associated wavelength associated with these electrons that was first proposed by de Broglie. And the de Broglie hypothesis was that these electrons, or particles of any type that we're dealing with, have a wavelength associated with them that is equal to h divided by its momentum, p. And of course, p is equal to mass times velocity. Right? So this is a calculable number based on the momentum. And furthermore, the confirmation that de Broglie was correct was that the observed angle for theta 1, we'll say theta 1, for m equals 1, was confirmed by calculating the angle based on the de Broglie condition that sine theta is lambda over d, and lambda is h over p, so this becomes h over d times p, right? And d, of course, should have drawn out here, is the spacing between the atoms, much like a diffraction grating. So this was a confirmation, and of course, this was observed, and this led to the conclusion that lambda equals h over p is in fact a valid assumption. We were actually able to calculate lambda and show that the angles at which we get a maximum intensity of the reflected electrons occur at this angle with this wavelength. Okay? So it confirms the de Broglie hypothesis that those angles of maximum intensity defined by this equation are in fact observed. And that was a validation that the concept that wavelength is equal to h divided by momentum is in fact a valid thing to say. Now we're going to do one more example before we move on to more complicated concepts, and eventually, hopefully, will leading to the Schrödinger equation, which I will plan to derive for you today and show you how it works. But the second example is in the handout, and I'll just draw it briefly. So the basic idea of there was an actual experiment, another real experiment, that was done with neutrons. And these neutrons, in your handout, this is a neutron beam, right? Neutrons. Okay? And so I always draw it like this because, you know, I can either consider these as particles or as waves, right? So with the squiggly song line, I'm looking at the wavelength of the particle. With the dots, I'm looking at the momentum of the particle, mass times velocity, right? So P equals mv. That's each one of these little dots is a neutron. Okay? And it's two adjacent pictures. I either think of it as particles or I think of it as a wave, but not both at the same time. Okay. So this was the picture we had. And in the handout, you see we've got a example with a screen 1 meter away. So the screen is 1 meter away. We see a diffraction pattern, and you'll see diffraction peaks like this. And these diffraction peaks are located at, I didn't quite draw the spacing exactly as I probably should have, but this spacing from here to here is, on the screen, was 75 microns. Oh, by the way, I didn't tell you a couple other parameters. The spacing D between the slits is 25 microns. And the wavelength, this lambda, which I can now, we're going to put on top of here so that you reinforces, this is called the de Broglie wavelength for the particles, is drawn like this. There's lambda. Right? And lambda, in the case that we're studying here, is equal to 1.85 nanometers. Now, on your handout, it says 18.5 angstroms. That's because the older units, which I grew up with, was in units of 10 to the minus 10 nanometer, 10 to the minus 10 meters instead of 10 to the minus 9. So 18.5 angstroms is 1.85 nanometers. Okay. So we have a wavelength, and by the way, we can now calculate the momentum of the neutrons, right? Because we have this de Broglie hypothesis, which we'll do in just a minute. So the observation is that the first maximum occurs at a distance y from the center of the screen. And as we've learned before, y is equal to L times tangent of theta, where theta is the angle to the point of interest. And I'm calculating, this of course is the intensity, and I can either call it intensity versus angle or intensity versus y, however you wish to call it. And so I can get intensity as a function of, for example, for y, right? And furthermore, we see that there is an intensity maximum, y1, at 75 microns. And by the way, the intensity maximum at y, for the second one is double that, so I get y2 is equal to 150 microns, right? And you can see that on your handout, that these peaks are spaced at 75 microns apart. Right? We now have an ideal case to be able to test the de Broglie hypothesis. Is lambda equal to h over p correct? Is this correct? Right? And we wish to test it. Is the way that in fact is the case. So what we can do now is to recognize that in the case of the first intensity maximum, for example, that I will have the condition that d sine theta 1 is equal to lambda. And by the way, this one over here will be d sine theta 2 is equal to 2 lambda. And this is the coordinates at which I can measure this. Now, because y is equal to L tangent theta, then this now tells me how to calculate sine theta 1. Right? Sine theta 1 is going to be equal to, and you will see very shortly that a small angle approximation is absolutely valid here, because if I calculate the tangent, then this says that y1 divided by L is equal to 75 times 10 to the minus 6, which is a very, very small number. So we know that sine theta equals tangent theta equals theta is a good valid assumption. So I can also say that the sine of theta 1, this would be, yes, the sine of theta 1 is equal to 75 times 10 to the minus 6. Right? Okay. Now, in order to test the de Broglie hypothesis, like we did with the electron beam, we have to use this equation right here and calculate lambda from this equation where that first peak occurs and compare it to lambda from the de Broglie. And if I get the same answer, then I know that my assumption is correct, that particles do have a wavelength associated with them that is given by h over p. And in fact, that's exactly what we're going to do. We're just 2 steps away now from actually demonstrating that. So let's take d sine theta 1. Okay, so d we said was 25 microns. So I have 25 microns. And I'm going to multiply it by sine theta, which is 75 times 10 to the minus 6. And I'm going to get a number which is 1.85 nanometers. Okay? Now, I told you that, in fact, that is the wavelength that's given to you in the text, right? That's given to you as the subtext on the figure. But more importantly, what is important is that this is not a measured value or a quantity that you can measure directly. What you actually do is create neutrons with a certain momentum. So the momentum of the neutrons is what I need to know in order to test the de Broglie hypothesis. So the momentum of the neutrons is what I know. In this particular case, the momentum P in units of eV over c is equal to 670 eV over c. Okay, that's the momentum of the neutrons that are impinging on the slit. Okay. From that, I can calculate this value of lambda, and we'll show you how in just a second here. So let me raise this up a little bit. I must put sandpaper on these rollers to keep them from moving. So in any case, what I could do, let's see how we actually use this equation. So lambda is equal to h over c. Well, I'm going to multiply I'm going to multiply the numerator and denominator by c, so I get hc divided by pc. And these are both going to be in energy units, which is eV, or units related to eV. We did this last time, and if we multiply h times c, this became 1240 eV nanometers, which we used when we were doing Compton scattering. And I'm going to divide that by pc. Right? Now I'm going to divide numerator and denominator by c. Okay? By numerator, then I get that this is 1240. This becomes equal to 1240 eV over c nanometers divided by p. So as long as p is an eV over c, I just divide it into 1240 and I get my wavelength in nanometers. Right? So we do that, and P is 670, so 1240 divided by 670 is about 1.85 nanometers. Right? So these two numbers agree. The angle at which, or the wavelength for which I would get a maximum intensity, the wavelength, lambda, for which I would get a maximum intensity, for double slit diffraction is given by 1.85. The wavelength that I calculate from the de Broglie hypothesis is 1.85. So de Broglie confirmed. So the kind of strange theoretical idea that this guy had before he wrote his letter to Einstein asking for approval turned out to be right. And it was basically based on the idea that this equation, lambda equals h over p, is true for photons and light. So in other words, in terms of the light phenomenon, if I'm talking about a wave of light, this is the wavelength of the EM radiation, right? This is the EM field, right? And P is the momentum of the particle, and this is the momentum P for the photon. So the equation relates the particle property of momentum to the wavelength of the electromagnetic field, right? And that was true for light, and so de Broglie said maybe it's also true for particles. Maybe particles which have some momentum also have some wavelength associated with it, unrelated to the electromagnetic field. It's just a particle, and a particle has a wave property, or particles will have a wave property. So that idea was hypothesized, and now we've just confirmed it twice. Okay? Once with electrons diffracting off crystals, once with neutrons diffracting through a double slit. Okay? So that settles the score. Anybody have a question on what this means? Because it's going to be very important as we go on. In the particle point of view, by the way, I can replace photon with neutron. Or if I'm using an electron beam, I'll replace the momentum with the momentum of the electron. Or if I'm using a proton beam, I'll use the momentum of the proton. Any particle, doesn't matter. Right? Wavelength is normally associated with the electromagnetic field, right? Because the wave the light wave is an electric field that's oscillating up and down in space as it propagates. I understand that. I can draw a picture of a wavelength of light. It's the electric field vector that is going up and down, and the amplitude of the electric field vector is going up and down. I mean, people, I'm assuming we've already talked about this. So this whole thing is moving with velocity c in space, and the electric field is oscillating, right? Now, up till now, I don't really know what lambda means for a particle, because there is no electric field. Well, at least not for neutrons, and it works for neutrons. And the indication is that the diffraction experiment will work the same, I get the same result, whether this particle is a neutron, a proton, or electron, as long as the momentum is the same. Okay? So it's only a function, whatever lambda is, which at this point we don't really know, it's only a function of momentum. And it does tell us how to calculate constructive interference and destructive interference from diffraction. Right? That much we know. That much has been confirmed. Okay, now let's stop for questions. Yes?
I just want to make sure, is it a double slit or is it the single slit for the neutron diffraction?
Both, but this one is double. Okay, this one is a double, and what you see in your on that sheet is for a double slit.
Oh,
it says on there, right? It says
single slit.
What? Oh, and I'm looking at the so the one that we're talking. We haven't gotten to the second sheet yet. The sheet we're talking about is this one with neutrons, and it's a double slit. Now I'm going to make the assumption that and not just the assumption, but it's been validated, that if I were to do the same experiment with a single slit, I would get single slit diffraction. And if I do it with multi-slit, I'm going to get multi-slit diffraction. And it's going to look the same as it does for a light wave, as long as the wavelength of the particle, we call this Broglie wavelength, is the same as the wavelength of the light that I did that experiment with. The results will be the same, as long as lambda is the same. So, okay, good question. Next question. I need a drink of juice. Not the other kind of drink. Yeah, that one would be great too. Okay, so are we clear so far? Do you have an idea what's going on here? Right? De Broglie was onto something. Okay, now we need to figure out what is the wavelength about. What is the meaning of the wavelength or of the wave? So let's go back, and now we'll go back to the other handout, which is this one right here. And let's suppose now we compare the light diffraction of a single slit with the neutron diffraction of a single slit. Now I could have done the comparison with double. I just chose single. Right? So single slit was just a random choice. Okay, so let's review how we got to where we were with light diffraction, right? So the thing you want to see here is that we start out with a sinusoidal wave propagating into the slit. The equation of a sine wave propagating is sine k over kx minus omega t, and the velocity of the wave, which in this case is c, is equal to omega divided by k. Right? That was that's the velocity of this wave. And we have a certain wavelength associated with that. That's lambda. Right? This is in fact an electric field wave. Right? It's an electric field wave. It goes through there and it produces this diffraction pattern that gives me a pattern that looks like this, and an equation that's described by the intensity in watts per meter squared per second. This is watts per meter squared. I'm sorry, that's not per second. There we go. Correct that in a second. Watts is already energy per second. I don't need to have the second there twice. So the intensity is in watts per meter squared. We had homework problems with this, and so you hopefully are familiar with that. And the y dependence, so the y dependence is this coordinate y as a function of this angle theta, right? And what we showed was that, or what we assumed from Maxwell's equations, is that the intensity is proportional to the square of the amplitude of the electric field. Right? That's what this quantity is. Now this quantity is the amplitude that comes from adding up the amplitudes from all the subslits that are all just a little out of phase with each other. And we had a phasor diagram that we went over to just derive this, and we got that E theta 0 was equal to the initial amplitude E0 of the wave times sine beta over 2 divided by beta over 2. Right? And this is the amplitude of the wave at this point, or whatever point I want to calculate, right? And if I want to know the intensity at that point, I square it and multiply by this constant. Right? That's what we did in the first month of the entire course. And of course, beta is a function of theta, which is also, and theta is a function of y. So I can get y from that, and so therefore this quantity is a function of theta or y, right? That's what we've been saying. That's what the diffraction equation tells us. How does the intensity change as a function of theta or y, right? You puzzled?
No, I'm fine.
You're fine. Okay. Yeah, sometimes I don't know if I'm beating a dead horse or it's worth reviewing. Drilling it in a little more, so erring on the side of caution. Okay, so this is our equation. This is what we have, and this is how we got the intensity. Now, notice, now I want to go and look at the particle property of the pattern. How do I understand this intensity pattern in terms of particles. Right? So in terms of particles, I've got photons coming in here, right? That's the particle picture of light, photons. So I'm going to have a certain number in photons per second. So this quantity is a certain number of photons per second coming through the slit, right? That's how many photons are getting through it, right? Then once I do this one photon at a time, then every time I get a photon going through here, it's going to arrive on the screen somewhere, right? It's propagating forward. It may arrive here, it may arrive here, it may arrive there, right? It's going to go in proportion to a probability function. In other words, most of the light intensity is in the middle segment here, so most of the photons are going to arrive into this envelope, which is where the intensity is the highest. But I can equally well call this intensity the number of photons per second times the probability that it lands at a given distance y from the center of the screen. In other words, the number of, and this probability y, by the way, is a probability, probability y is a probability per unit area or per meter squared. So this is probability per meter squared, and I still have photons per meter squared per second. If I'm looking at it one photon at a time, it either goes here, it goes there, it goes, okay, so let's say it goes here, right? Then the next one goes through. The next one comes in and it arrives there. The next one comes in and it arrives there. You keep doing this and the statistics are adding up on the screen. Right? They're adding up on the screen, and I'm going to find that I get more photons right along in this region than I do over here, and I get more photons here than I do, let's say, here. And if I do it for enough, keep throwing enough photons through, eventually I build up the observed intensity pattern. Okay? And I now have explained the intensity pattern in terms of the particle property, which is the number of photons per second coming through the hole, through the slit, times the probability that's going to land at some location y. Right? But these two expressions, which is which I will come back to in a second, but this, of course, this is what I would call this is what I call the photon interpretation, right? This is the photon interpretation of the screen. How do you spell it? Interpretation. Of what's going on. On this side is the wave interpretation. I've derived the intensity on the screen based on the amplitude of the wave. Right? And the result is in watts per meter squared. Now, if I divide this quantity, watts per meter squared, by the energy per photon, HF equals the energy per photon, okay? Then the result is that this becomes photons per meter squared per second. Right? If this is in joules per second, then dividing and I have 1 joule or x joules for every photon, then I simply divide that in here, and now I've got photons per meter squared per second. So I've been able to convert from watts per meter squared per second to number of photons per meter squared per second. In other words, now I'm looking at the density of the photons on the screen. And I do that just by dividing by HF. But they have to be the same. In other words, the intensity that I derive from this point of view has got to be the same as the intensity I get from this point of view, because I'm describing the same intensity pattern. Right? And they both have the same units. So now what I could do is, what I do is I solve this for probability, and I get that probability P of y is equal to a bunch of constants, and I really don't care what they are right now, but I think sometimes people like to have them in there so that they can maybe study it later in their notes, times the square of the electric field amplitude squared, which, by the way, is a function of y. So remember, this was equal to sine, well, it's right here. It's equal to that, and beta is a function of y. So this is basically a constant, we'll call this a big constant, c times the square of the electric field amplitude. That's the probability of finding a photon at a given location y on the screen. And I do it simply by equating the wave picture of the intensity pattern, which is in terms of the amplitude, with the particle interpretation of the intensity pattern, which is photons per meter squared per second. And so now what I get is that the probability is proportional to this quantity. So probability is proportional to the amplitude of the wave squared, right? Is the amplitude of the wave squared. And that's an important thing to keep in mind, and that comes just out of the photon interpretation of the electromagnetic wave, right? This is the electromagnetic wave, this is the photon interpretation, these two are equal, I solve for the probability, this is a single particle probability, right? This is it's important to give a single photon probability function, single photon probability. Right? I'm putting this many photons per second through, but every time I send a photon through, it lands on the screen that's dictated by this weighted probability. In other words, most of them are going to lie between here and here. Most of them are not going to lie out here. So this is just a probability function. Right? Every photon is, each photon goes to the slit and it has to decide where to go. It can either go straight ahead, which is what we would think if it didn't diffract, or it starts now acting like a wave. Now if you think about the wave pattern, well, light waves bend as they come out of the slit, so some of them are going to come off this way and some of them are going to come off this way. And some of the photons are coming off this way and some this way. Right? But they're not all equally weighted. Most of them curve off in the center and they follow this probability function. The most likely place for the photon to arrive is dead center right down the middle with no deflection. Right? That's the most likely thing to happen. And that's sort of what you see when you have a shadow, right? If you put light through a slit and look at the shadow on the wall, it goes straight through. The most likely places to see the light is straight ahead of the slit, not off at 90 degrees. Okay? So it's a probability function. Okay, anyone question? Is this clear? No. You're shaking your head. No, it's not clear. Is there? Yeah.
Is n gamma a constant?
Yeah, well, it's an adjustable constant. It's the intensity. It's how many. One way to think of intensity is how many photons per second is hitting your eye. Right? I mean, when things look brighter, it's because there are more photons per second coming through. I can always dim or strengthen the light source. Right? But once I set it, yes, it's constant. Okay. This is very critical. It's the interactive play between looking at a phenomenon from the wave point of view and then looking at it from the photon point of view and saying the two must be the same when I get to the final result. And the final result is the intensity looking at it from the wave particle point of view has got to be the same as the intensity when I look at it from the particle point of view, because intensity is energy and the total energy is conserved. The energy that I get on the screen should not depend on whether I look at it from the photon point of view or the wave point of view, because if it does, something's wrong with the theory. It's inconsistent. Then that would say that one of those interpretations was wrong. Interesting logic. Huh? Okay. Any other questions? Yes?
I have a question. How would you have minima? Right? How would you have
you be a minute for light. We're talking about light right now.
as a photon?
As a photon, you can't. You you basically say there's a probability function that I have calculated from the wave property. There's a probability function that I have calculated from the wave property. In fact, I can only actually predict the minimum as a wave by looking at the wave. I can't predict the minimum by looking at the particle. That won't explain it. I mean, light either acts like a particle or it acts like a wave. I can detect them as particles, but there are certain phenomena that I can only explain as a wave. And those minima are one of them. Where the minimum, where the maximum. That's purely the wave phenomenon. But if I'm doing the photoelectric or Compton scattering effect, I can only explain it by looking at it as a particle. As light as a particle. So it's like an interplay. It's like your mind has to be able to adjust. Am I looking at the wave now, or am I looking at the particle? Which way is it operating like? Which way is it operating? Good question. Any other questions? Any other questions, friends? It takes a while to absorb. That's why I gave you this handout. Hopefully that will help. Okay, so we're ready to move on. Try something. Go take one step, baby step further. Now let's look at what happens with neutron diffraction. Right? With neutron diffraction, I only have the particle field. Well, I have two things. I can think of it as particles, which obviously that's what we do, right? We think of electrons, protons, and neutrons as particles. But there is something that is wave-like in this whole thing, which is this lambda. And this lambda is, by de Broglie, is h over p, but we don't really know what it is. But what it's looking like is that it's still predicting how I get this intensity pattern, right? Because I get this intensity pattern by summing up light from all the subslits that come through the slit. So there's something wave-like going on because I get a pattern on, and I do the same experiment as I did up here, only instead of letting one photon get through at a time and fall on some probability map, I'm letting one neutron through at a time. And it falls on the same probability map if lambda were the same in these two cases. And I can do that. I can make lambda the same. Lambda is a controllable. I can either select the wavelength of light or I can select the momentum of the particle. Right? So I can always make the lambda for the light equal to lambda of the particle. Right? Okay, so I do the experiment. Okay, and now how do I describe intensity for neutrons on the screen? Well, I would describe it in the same way as I did for photons. It's how many neutrons arrived at this particular little point, and let me draw a grid out. So supposing that if I look on the screen, I actually have a grid, and neutrons, because of the way we've, see if I do this right. Okay, so let's call this dimension, we'll call this dimension z, for example, and this dimension y. Okay, y is the vertical axis. Then every photon that gets through here is going to land in one of these squares. It's going to land here, it's going to land here, it's going to land here, right? And every time I let a neutron through, it falls somewhere on that screen. But the most likely place it's going to fall is between here and here, between these minimum. By the way, these minimum occur at sine theta equal to plus lambda over d, or sine theta equal minus lambda over d, right? And most of the neutrons are going to fall within those limits. The most likely place for the neutron to fall is straight ahead on the screen, right here in the middle of the screen. That's the most likely place for it to fall, right? So I'm basically now going to do is say that if I do this enough times, and every neutron has this is its probability function. So this is a probability distribution, just as it was for the case of light. This is a probability distribution for each neutron, then it's going to land in a way that is populated exactly with the probability weighting that I had before up here. And furthermore, because this is acting like a wave, and I get waves that are adding up with certain displacements, I can say that the amplitude of the wave is exactly the same as I had before, with this amplitude E0 here replaced with this amplitude A, and the rest is the same. Sine beta over 2 divided by beta over 2. Okay? And if I square that, then I get the probability of where it's going to land. Whether it's going to land here, it's going to land here, land here, land here, land here. It'll give me the probability distribution, right? So I end up by saying that that the meaning of the wave. So I've driven. So first of all, I write out what is a wave of neutrons look like. Well, it's going to have the same form as the wave of the electromagnetic wave. It is a wave moving through space. It's sine kx minus omega t. It's not moving at the speed of light, however. But it is this is a moving sine wave. And it has wavelength lambda. Right? Now, if I do the substitution, then I get that k is equal to 2 pi. This is on your notes already, so you shouldn't have to write it down. 2 pi over lambda. Omega is equal to h, 2 pi times the frequency. And the quantum, the de Broglie condition is that lambda is equal to h over p, and f is equal to e over h. Okay, I'm sorry, e over h, and, did I get it right? Yeah, e over h. Like this, okay? And E is equal to 1/2 mv squared. That's the kinetic energy of the particle, and P is equal to mv. Right? And if I place these values into this equation, I get this equation that psi, which is the wave equation for the de Broglie wave, psi of x and t, is equal to A times sine of px minus et divided by h bar. Now h bar is a unit that it's another abbreviation that we will have to get used to a little bit, but the definition is that h bar is equal to h divided by 2 pi. And it shows up so much in our calculations that we give it a special name, h bar. So h bar is just h divided by 6.28, right? This is a very simple equation. It's not much more than just what we see than this one. But what's important is that the wave equation for the particle, or the neutron, consists of the momentum of a particle property, the energy of the particle property, to give me the wave property of the particle. So the wave equation, this is the wave equation for the particle, this is the wave equation, has the momentum and the energy of the particle. Okay? So I have a wave equation that describes the motion of the wave that's moving with the particle in terms of its momentum and its energy. Okay. Something we'll come back to in a second. Back to this point right here, what we see is that the interpretation, what do we mean? What is the interpretation of psi, of the wave amplitude, or in this case, the wave? What is the interpretation? The interpretation is that the square of the amplitude of the de Broglie wave is the probability of finding the particle at a given location x, at a given x and time t, right? That's the interpretation. That for particle waves, that this square of the amplitude, we denote this as the probability of finding the particle at position y is proportional to the square of the amplitude of the wave. That's the fundamental interpretation. So what does lambda mean, or amplitude? Well, lambda is, this is now, we call this a probability wave. In other words, it's a probability wave. In other words, it's not a wave, it's not a wave like an electromagnetic wave. There's no electric field associated with it. There's no disturbance of the medium from this wave. There's no pressure propagation through a medium. It is simply a probability function. It is a function that tells us, describes, how do we find the probability of where a particle is going to be located? Okay? And the reason, and it comes out of this, I mean, it all comes out of this equation right here. By comparing with what we know with photons and light, we apply the same logic for neutrons and its wave, and we say, oh, its probability must also be proportional to the square of the amplitude of the wave. And that's how we get the interpretation. Any questions? Isabel? I picked her out. Did you have a question? You have a question. Charles, do you have a question? No? Okay. Mark? Mark, no? Okay. All right. I know it's a little lot to absorb. It's actually better the way I explain it than the way Katz explained it. I think Katz doesn't do a very good job, but Giancoli does a little better job. And his book is in the math physics library, or it may also be at Founders. I don't know. I haven't been over there, but I think he does a little bit better job. Okay, so that's what we end up with. Now what we're going to do is go back. Now we're going to try to work towards getting to the Schrödinger equation. And what we're going to do now is go back and say, let's look at this part of the wave before it hits the slit. Let's focus on this equation right here and see what it really means in terms of probability. Okay? Let's try to describe how to interpret that in terms of a probability function related to some real physics experiment or setup. Right? So I'm going to give you a setup that I think is not a bad one to look at. Let's suppose that, remember we talked about heated filaments to boil off electrons and to make an electron gun, so to speak. And we know that a heated filament will, in fact, does emit electrons. They will come off with some very, very small velocity. We also know, based on when we started talking, we talked about this last time, that if we design an electrode so that there is an accelerating potential, so I put this electrode at positive potential, then what will happen is that when I have a switch, right? I have a switch right here. When I close this switch, oh, and by the way, there is a heater coil, so there's a power supply for current to heat the coil, right? So I have to have some current flowing through this thing to get this hot. Once this conductor becomes hot, then the electrons are actually boiled, in fact, leave the surface. And that's how we make electrons. Okay, now, let's suppose that I put 100 volts on here, and we talked about this last time. Then as the electrons move from here to here, they will acquire a kinetic energy of 100 electron volts when they leave, when they get through the hole. Okay? And this is the kinetic energy. Right? Now let me suppose that the switch only closes for closes for 1 nanosecond. So let's say we do delta T equals 1 nanosecond, right? So, and let's suppose further that with this 100 eV, that the velocity of the electrons is, which you can calculate, is about 0.02 times the speed of light, c. Okay, so I briefly close this thing and then I open it again, right? But I have the intensity so low that only 1 electron gets through, right? 1 electron gets through, and now I need this space again, so I'm gonna have to erase the top. 1 electron gets through, and all I know is when I shut the, when I open the switch again, that the electron can be somewhere between on the x-axis, that we described here, that the electron could have been emitted when the switch was originally closed. It would be up here, or the electron got emitted at the end of the pulse, which was down here. So I have only 1 electron that gets through, and the length of this pulse is going to be equal to V times the time delta T, the time that was left over. V is equal to 0.02 times C, and so X is equal to 1.8 centimeters. Right? So I have what I might call a probability pulse. Right? All I know is that the electron it could have been emitted at the instant that I closed the switch, or it could have been emitted right before I opened the switch. Because at that time, the voltage is turned off, and I no longer have, I should switch this to ground, by the way. So I have 2 switches here. One is to ground, and one is to, so we'll call this terminal A and terminal B. So we can either close the switch over to ground, or I can close it over to here, which is to the battery. So when I normally it's connected to ground, but for 1 nanosecond it's connected to here, and the electron is somewhere in this envelope, right? But I don't know where, and it could have come off any time with equal probability. Right? Well, if there's a probability function that's associated with this equation, then the first thing I'm going to do is say, okay, well, probability as a function of x and t is equal to the square of the wave function, psi of x and t squared. So this is a squared times sine squared of px minus omega t divided by h bar. Okay. Now, if I plot this out at a given time versus position, then what I get, what does a sine squared function looks like? It looks like this. Okay? That's what a sine squared function looks like. This is sine squared as a function of x, and I'll do t equals 0. Right? For example. This is clearly not the probability function that I want to describe. I want to describe a probability function, p of x, that's flat all the way across here with equal probability. There is no reason why there's 0 probability at certain locations when the electron could have been emitted anywhere. Right? So this will not work. But what does work is if I replace this sine function with what we call a complex wave function, or a complex wave function is probably the right word. And this is e to the I px minus et divided by h bar. Same argument, right? And one of the reasons why this is very similar to this function is there's something, oh, by the way, I squared is equal to -1. I is a complex number, and I is the square root of -1. And that's not a real number, but it's a real mathematical entity. It's just not a real number, but it's a mathematical entity, right? So what are the features that this thing that is useful for is that you can express that any function e to the I theta, right, is equal to a complex number that is cosine theta plus I times sine theta. Right? And this has the form of a number which is a plus b times I. Right? Sorry, we have to do a little bit of complex analysis here to get you up to speed, because the Schrodinger equation has the square root of -1 in it. And there's a reason for that, so we have to actually get there to have some understanding for it. Now, this is a complex number, a plus bi. I can plot a complex number in terms of its real and its imaginary form. So I'm going to take the real part of psi over here. I'm going to say this is a, and this is now my new function, psi of x and t. Okay? And this is the real part of psi, and this is the imaginary part of psi. Okay? And it has a real part that has length a, an imaginary part length b, and the amplitude of an imaginary number, a complex number, is a squared plus b squared square root. Right? That is the amplitude of, this is the amplitude of a complex number, a plus bi is equal to the square root of a squared plus b squared. Okay. All right. So this is a way of writing this. I can also, by the way, get this by if I take a plus bi and I multiply by a minus bi, this is called the complex conjugate. Right? So I'm going to, this is a complex conjugate. In either case, this is equal to, you can do this math for yourself, this is equal to a squared plus b squared. Right? But in this particular case, a is cosine, b is sine, so the square root of the of these two quantities, a and b, is sine squared theta plus cosine squared theta, and that is always equal to 1. Right? So what I have now is that the complex amplitude e to the I theta is equal to 1. Okay? I now have a complex wave function. I have a oscillatory wave function. I still have the cosines and the sine, right? Theta, by the way, is simply what's in here. But it's a complex number. And it oscillates in the real and imaginary parts separately. Okay? But it has the feature that this is equal to 1 for all x and all t, all time, all x and t, right? Okay, so I now have a wave function for here. It's now a e to the I px minus omega t divided by h bar, and, I'm sorry, this is equal to psi of x. Right? The probability p of x is going to be equal to the square of this, a squared. And now I take the amplitude squared of the exponential, and this is equal to 1. So this is simply a squared. All right. So now what I'm going to do is calculate the how do I determine what a is supposed to be here? What the coefficient, the amplitude of the wave? Well, what I can do is say that the probability that the electron is somewhere has to add up to 1. In other words, we know the electron is either here, or it's here, it's somewhere in this box. Right? So the integral of the probability, p of y, dy, from 0, say for example 0, to, we'll call this x0, to x0, must add up to 1. So 0 why did I do y? I'm sorry. We're in x. P of x dx, x0 is equal to 1. P of x is a squared. So I get that a squared times p, the rest of it is simply 1. The integral of unity from x0 to 0 is simply x0. That's equal to 1. So I get that a is equal to 1 over the square root of 1 over x0. Right? And this is my normalization constant because the probability has to add up to 1. If psi represents a probability wave, then the probability has to always add up to 1 if there's only one particle in that envelope. And we've assumed right now that there is only one particle in this envelope. Okay? So we have to generalize the wave function to a complex oscillatory wave function that's given by this. We can no longer simply use the sine and the cosine to describe a moving wave. It has a real part that is sinusoidal, and it has an imaginary part that's sinusoidal. But it can't be described by simply a real wave anymore, a real sine function. And it's sort of for this reason. Okay, that's a lot to cover. We're 2 steps away from the Schrodinger equation. The Schrodinger equation is actually trivial from here. It is actually trivial. And any questions though before we move on? Any questions you want to ask? Okay, what we're going to do is describe a differential equation in which this is the solution, right? And you might say, why would you create a differential equation when you already know the solution? And the answer is because we're going to generalize the equation to cases where I don't know the solution. Okay? So we're going to start with the cases where we do know the solution, which is this equation right here, and this is the wave equation for de Broglie wave. Okay? This is now the new wave equation, not this one, right? And not that one. Okay. Now, the way we do is pretty simple. Let me choose a equals to 1. So I'm going to, and now by the way, the result does not depend on this, but I'm going to choose a equals 1 because it gets rid of the constants that I always get through when I make derivatives and do the calculations. You can go back later and show that it's true even if a is not equal to 1. But let's make the algebra simple. So now what I'm going to do is, what I'm going to notice is that anytime I take the derivative of an exponential, and it doesn't matter whether this I is real or not, it's still a constant, right? So when anytime I take the derivative of e to the ax, I get, or let's say ax plus c, ax plus c, where a and c are constant, then I get that this is a times e to the ax plus c, right? That's the derivative, right? Okay, so we're going to take the derivative and indicate a little bit what we end up with here. So let's take the derivative of psi with respect to x. If I take the first derivative of this thing right here, I get ip over h bar. I get ip over h bar times e to the I px minus et over h bar, right? That's the first derivative, right? Take the second derivative. The second derivative, and by the way, I'm going to use partial derivatives because typically this is psi is a function of x and t, and if I hold one variable constant, then it becomes a partial derivative. So what I've just drawn here is actually what we call the partial derivative of psi with respect to x, which is equal to this number, right? Which is equal to this quantity, I'm sorry, right? Now I take the second derivative. The second derivative, psi with respect to x, and I squared is minus 1, so I get minus p squared over h bar squared times e to the I px minus et over h bar. Okay? I just took took another derivative. All right? Let's do it with respect to time. The derivative with respect to time, d psi by partial of psi with respect to time, is, now I'm taking with respect to time, so I get a minus IE over h bar out front over h bar times e to the I px minus et over h bar. Right? Okay? Now, let me multiply this equation by IH bar. All right? So I'm going to say IH bar times the first derivative of psi with respect to time is equal to E, which is the kinetic energy, right? E is the kinetic energy. We said E is the kinetic energy. Somewhere I wrote that down. Maybe I already erased it. So E is the kinetic energy. And this is E to the little e, exponential E, px minus et divided by h bar. Right? Now, let's multiply this through by h bar squared minus h bar squared over 2m. So I take minus h bar squared over 2m. And I'm trying to get a quantity that looks like p squared over 2m because I know that E is equal to p squared over 2m. That's the energy momentum relationship for a particle, right? So I multiply this by that, and then I get that minus h bar squared over 2m times the second derivative of psi with respect to x is equal to p squared over 2m times e to the I px minus et divided by h bar. Right? Okay. Now, one thing I know, since p squared over 2m is in fact e and the exponential are the same, these two things are equal. So these two sides are equal. Right? So the wave equation becomes minus h bar squared over 2m times the second derivative of psi with respect to x and equals I h bar times d psi by dt, in which it happens to be true that I already knew the solution, right? I created this as something in which I know the solution, right? However, I'm not always going to know the solution is equal to that because this is a consequence of basically saying, oh, this is p squared over 2m times the second derivative of psi with respect to x. I'm sorry, I said this wrong. This is p squared over 2m times psi equals energy times psi. Right? I over h bar, this is equal to energy times psi. So what I basically have said is the reason why this is true is because E equals p squared over 2m. So far, all I've done is saying the Schrödinger equation is basically stating conservation of energy, or what the energy is. Now what I'm going to do is say, well, okay, but this is all for what we call a free particle. A free particle means there are no forces. Right? F equals 0. There are no forces. It's at a constant velocity and it stays a constant velocity. But now I might actually have a force acting on it. Right? And so what happens if I have a force acting on it? Then I have to include potential energy term. Right? And the equation that we know about force and potential energy is that force as a function of x is equal to minus the derivative of the potential, u of x. Remember that from your mechanics course? That force can be described as the derivative of the potential energy. Right? This is from 253. Right? This is an equation from Physics 253. So if you're not familiar with it, you need to go back and do a little bit of review. All right? But what it now allows me to do is to say, oh, well, if I want to put a force term in here, one thing I know is that kinetic energy plus potential energy is equal to total energy. Right? So let me insert a potential energy term in here. and I'm going to add it to this side, and I get that p squared over 2m, right? Times, well, let's do it this way. This is the kinetic energy term, right? So this is the, yeah, let me do it this way. So this is p squared over 2m times psi plus u of x times psi is equal to e times psi. Okay, so let's go back and now let's finish this up. So now I go back and substitute what p squared over 2m is. It's this derivative. So I can replace that with h bar squared over 2m times the second derivative of psi with respect to x plus u of x times psi is equal to the energy times psi. And psi is a function of x and t. So now I have an expanded equation for psi. And in general, if there's a force acting on a particle, I am not going to know what the answer is until I solve this equation. Right? So this becomes what's important. And furthermore, once I solve this equation, then I can say that the probability of finding the particle, oh, we're doing it versus x, right? The probability of finding the particle at a given distance, point x on the x-axis, is going to be equal to psi of x and t, but we will say x and t, quantity squared. Okay? This is the Schroeder equation. Okay? And this is what it means. Okay? It's going to give me the probability density because one of the things that I always have to happen that's going to have to be true is that the integral of the psi of function x of t, quantity squared, integrated over space, over distance, from minus infinity to infinity, must add up to 1. Or times a constant. Put a squared. But the probability, the integral of the probability of p of x over space, the particle has to be located somewhere. So this probability has to always be equal to 1. Because the particle has to be somewhere. The particle has to be somewhere. So this is going to be very helpful to solving equations, problems, by knowing these facts. That this, of course, is the equation, this is the meaning of psi, and this is a condition that because psi squared is a probability, that the integral of the probability has to be equal to 1 once I add up over all possible regions where it could possibly be. Because there is only one particle and it is somewhere in the room or in space for the problem we're solving. Okay? All right, that's a lot to cover. That's all I have for now. My suggestion is to get as much of the chapter 40 homework done as you can. Begin reading chapter 41. I don't think it's as good as my explanation, but it's all we have. Right? G and Coley is also a good one as well. We will resume after spring break and have a good spring break.